work for Micron, and a lot of people may be going, why is a memory company here talking about RISC-V processors? It's a good question. And as we know, technology is moving, and you hear the term near memory, et cetera. So what I'm going to do is address one aspect of what perhaps near memory means. Later on today, there'll be a presentation by Tony Brewer who will discuss some implementation aspects of near memory on a DARPA-funded project. And yesterday there was a poster session by Trout on doing sorting in memory. So we're now moving into a new regimen of what does it mean to have memory and processing intimately involved. Anyway, here's the presentation. I have an extensive set of references, and I should point out I'm going to make sure I end in time with questions. So my good old friend Matteo will start on time for his keynote speech, very important. So I'm actually going to use these terms architecture 1, 2, 3, etc. And I reference this from a recent paper by Mark Hill. And Mark presented a paper detailing the recent security breakdowns of Spectre and Meltdown. And in his paper, he discusses this notion of architecture 1.0, which I found very, very interesting. And talks about speculation, pipelining, clock cycle flat, and that's certainly a characteristic. The other interesting part of his, not part of his paper, but consistent, is a paper published by Stan Williams of HP. He was one of the creators, inventors of Memristor. And you can read it yourself. And if you go to any architecture conference, people always talk about clock cycle is flat, how do we get more performance? We saw yesterday in the presentation on Matteo's supercomputer that they increased peak performance by over 10, but only got 30% more performance for the applications. So that's a real problem if you're trying to get more performance. And I'm going to try to address that. Tony will address it. And the key is we have to be more creative. The easy increases in performance are done. So in Stan's metric, he goes, the world previously, and this would be architecture number 1, was very processor-centric. So you see CPUs and the memory was attached, and that's pretty good representation. Maybe you can call it a cluster or whatever. And what he says is, going forward, it has to be, and this has nothing to do with RISC-V, by the way. This is just a particular view of how things are going forward. As you can see, open architecture, RISC-V, ARM, etc. And every time I look at it, I go, this is really, really true. And what makes it even more current, and this sort of came out yesterday about these architectures, is there's no IBM mainframe. So that shows you how appropriate this presentation is. And architecture 2.0 is not just the ISA, but what does it mean to have security? And we've seen a lot of papers. So, there are a lot of evil people out there. And we hear things, covert channels, side channels. And some of these can be addressed, some can't. And we'll go into some of these going forward. And the key here is it's a memory-driven computing world. That's where the world is going. And what does memory-centric mean? Numeric processing is trivial. 20, 30 years ago, we would spend days, weeks figuring out how to do multiply and divide. Today, we take an IP block, we're done. It used to be price performance, now it's price performance per watt for efficiency. Achieving efficient memory access is very, very hard. And memory references possibly will not be homogeneous. And what I mean is, it's not just going to be RAS-CAS. We have to figure out what does it mean to have some intelligence referencing to memory. And as we'll see later with some of the security is that caches now have to be protected memory state. Moving ahead, I presented this a year and a half ago, and in discussions yesterday, we're going to start now a task group, working group, to define RV128, and I will be the chair of it. And we'll figure out what the charter is and the co-chair. You've heard a lot of people talk about 128-bit addressing, 1,000,000 cores, and things like that. And I think I know how to do it, so I'm going to give you some idea of how I think I'm going to start approaching it. Well, the first thing is I have to be able to address more than an exabyte of storage. That's the first thing. So, you know, we can debate flat versus segmented, but since I have government money to do this, there's no debate. We're doing it segmented. And you really, for protection and other things, want to do this. And when I did this, I just realized, and we'll see this later, is this also helps you converge with communications. If I look at IPv6, it's not a flat 128 bits. It's 64 bits and 64 bits. And we'll get to what that could mean later. But anyway, indexing is 64 bits, A of I. This is ISA independent, persistent across time and space, etc. Now, because it's ISA independent, if I go back to the previous diagram of memory-centric, as long as all the processors have the same virtual address space, I can pass pointers back and forth between processors. And I think going forward, that is a very desirable thing to do. And just for memory, I could spend several hours on this, but basically, it's an ACL-based memory system that has various bits to do a lot of things. You could see the presentation of a year and a half ago if you want to see more details about that. Okay, compatibility with RV64. We still have to live with existing programs. And the way to do this is even on an RV128 system, you have to be able to execute RV64 A.outs, so you have that level of compatibility. You have to be able to map 64-bit virtual into 128-bit virtual. And you have to have system calls in 64-bit space go to intermediate call level to convert to 128-bit calls to call the kernel. Now, for those who may say, oh, gee, that's difficult, whatever, this is something I did over 30 years ago, so this is relatively easy to do and define. And because of this, that means you can start off day one with RV64 utilities like editors and stuff to create your file without having to convert to RV128. Okay, it's actually very simple. You take RV64, and in 128 bits, you take an object and statically say that's 1, and R1 means RV64. And when I did this, I said, gee, I'm not sure I want to have statically defined objects. And I realized in communications, IP world, they do that all the time. We may have like an IPv4, we all know that 192.168 is my local network. And I could have a million external networks, but every local network is 192.164. So this is just the analogous of it. Secure architecture. So for example, object 0, I say is kernel static, 64 static, and we'll see why this helps us. And now we'll talk about encrypted memory, Spectre, Meltdown. So encrypted memory. We've had a lot of discussions about encryption, whatever. My view is one of the characteristics of an object, that's why you want to have smarter memory, is that the memory is encrypted versus not. Another aspect is how do I deal with multiple keys with teams? I have 50 people in the team and one person just leaves, but I don't want to change the key, so how do I permit the other 49 people to access the data? And there are various ways to do that. I reference 3. Okay, let's get down to some real meat. Spectre. I took this out of Mark Hill's paper, to give credit. And you know, you can read it, speculate, and we're going to come back to this. When you have a flat address space, that's inherently insecure for a lot of these things. So What's the fix? And the whole idea is to reference the kernel space. Well, if you're not in kernel space and a kernel has an object equals 0, the logic says, can't speculate, you're done. You don't have to look up in a table of what your access level is. The other aspect is all caches have speculative state, and I'll go into this in detail, which is different than the operational state. So the key is to start separating states between operational and speculative state. Branch target, and this is from the Google. And again, you can read the information. So a simple way to do this is to have multiple branch target caches. And every time I call a subroutine, I give a different branch target cache. So therefore, I don't disturb the state of the one who's calling me. A unique branch target cache state for each subroutine, etc. Meltdown. Again, you can read this, and the key here is, again, this is from Google, that it's because of a flat address space, I can look at it and you can't figure out where you're going. And it is alleged way back when that some evil people from Data General looked at VAX and said, gee, they could do that, I could do that to them. And it turns out they were right. If you could pass an address in a system call with some weird indexes, and this is the key, it's not to learn the secret, but you crash the system. So part of security is not just learning the secret, but causing something bad to happen. And of course, in contemporary security, Stuxnet is a great example of that. It wasn't to learn what they're doing, but to prevent something from operating. And again, indexing is 2 to the 64, so you can't go over. When you call an object call, you can look at pass pointers, and if the pass pointer has an object 0, it's rejected. So there's all types of things that are relatively easy to do. Shadow stack, a lot of times you hear all this heap overflow and how they obscure things. Again, with some actually relatively simple hardware, you have your own private set of stack pointer, frame pointer that you can't overwrite. And the data is in a separate domain, and go at it. You can't change the return block, you can't change other things. And unfortunately, what you have to do is deal with these things one at a time. I mean, you develop a structure, see what happens. I'm very curious to see this latest set of security attacks, these 8 of them that haven't been announced, to see when they're announced, how relevant this is. Are there changes? I certainly expect changes. So summary, what is architecture 3.0? One, we have to finish 2.0. So what I'm describing, RV128, is 2.0. Another thing which people tend to ignore is there's a lot of language-based security of verifying your program is written correctly from a security perspective. So what I tell people is you should have in procurements that the next release of Linux or this thing has to go through various levels of compiler verification. We all have to go back and read the seminal paper in security by Sulzer and Schroeder in 1975. Read it 3 times, read it 4 times, read it again. Then, as I call it, big words say technological singularity and security supremacy. I have no idea what that means, but that's a good tagline going forward to achieve these objectives. Thank you.